In this video tutorial, we will be discussing some of the quantitative conventions that we use in chemistry. This includes scientific notation, significant figures, accuracy versus precision, and SI units, also known as the metric system. First, let's do a review of scientific notation. This is Avogadro's number. You will be using Avogadro's number for the rest of your chemistry career, however short or long it may be. But in this unit, pretty much every question is going to deal with this number in some way or fashion. I think it's obvious why we don't want to use this number in this particular form. It is just way too large and unwieldy to use. There must be a better way to express this value. And there is, using scientific notation. Now, I could write 100, or I could write 10 times 10. I could write 1,000, or I can write 10 times 10 times 10. I could also write 10,000, or I could write 10 times 10 times 10 times 10. But writing it this way doesn't really give you any additional benefits, does it? So instead, I can write using exponents. 10 to the power of 2 is 100, 10 to the power of 3 is 1,000, 10 to the power of 4 is 10,000. By using exponents, we can tell the reader about how many zeros are in the number without actually writing these zeros in. So now I can express this big giant number in a more practical form. So scientific notation has the following format. First, it must be a single-digit non-zero number. So it must be a single digit. You can't have 2 or 3 or 4 numbers here. It's just 1. Now, if you did need this number in the front, you would simply just move this decimal over here, and now you would have a new single digit in the front. But let's move it back. Now, this single digit cannot be a 0. That's the whole point of scientific notation, to get rid of the zeros. So it is a non-zero value, followed by the decimal point, and then the rest of your number, whatever the value happens to be. Then it goes times 10 to the power of however many decimal places we need to move it. So how we write numbers normally is called standard notation. But as we saw previously, it can get quite big and difficult to use. So let's follow the format for scientific notation. Going from left to right, the first non-zero number I get is a 3. So I write a 3. This is then followed by the decimal, and then the rest of the values, ignoring the zeros because we're trying to get rid of zeros. So just the 729. Then we write in times 10 to the power of, and now we need to find out how many decimal places we need to move. So looking under standard notation, I don't see a decimal place. If you don't see a decimal place, we always assume it's at the end. So here's where it is, and here's where it needs to be. And it needs to jump 1, 2, 3, 4, 5, 6 places to get to between the 3 and the 7. So the exponent is a 6. Now, if this number is greater than 1, you must use a positive exponent. If this number is less than 1, we use a negative exponent. So positive exponents to show that it's a very, very big number. Negative exponents to show it's a very, very small number. In this case, it's a pretty big number, greater than 1, so we're going to use a positive 6. This just tells us which direction we're going to have to move the decimal place to get back to standard notation. Let's try this one for instance. So going left to right, the first non-zero number I encounter is the 7. So I write down 7, followed by the decimal, and the rest of the value, 157. Then we go times 10 to the power of, then we count how many spaces we need to move in order to get the decimal from where it was to where it is. In this case, it's 9. But because this is a number that's less than 1, so it's a tiny number, I must use a negative exponent to show that this is overall a small number. This also tells us in which direction we need to move the decimal to go from scientific notation to standard notation. So when we see a negative exponent, we move the decimal to the left in order to make it smaller and smaller and smaller, and then fill it up with zeros. While a positive exponent requires us to move the decimal to the right and then fill it up with zeros in order to make it a bigger number. Now just be careful when you're moving your decimals that you're counting the spaces in between. A common mistake students make is counting the actual digits themselves, but that doesn't make sense because does the decimal actually land underneath the number? No, it should be between numbers. So make sure you're counting in between the numbers. Alright, now what if I want to go from scientific notation into standard notation? Well, it's just a matter of moving decimals then. The exponent says 10 to the power of -4, So I know I need to move my decimal point 4 spaces. But should I move 4 spaces to the left or 4 spaces to the right? Because the exponent is negative, that tells me my value should be less than 1. But moving the decimal to the right would give me a value in the tens of thousands, so that can't be right. I have to move it to the left to make this a smaller value. So after making the jump 4 times, I can now fill in the empty spaces with zeros. So 0, 0, 0, 0. Let's remove my rough work and clean it up. And there's my value, 0.0003712, or in a more condensed fashion, 3.712 times 10 to the power negative 4. Now if this had been a positive exponent, I would move to the right, because the number indicates that it must be greater than 1. So pushing it 4 jumps to the right, filling in the empty spot with a 0, and then cleaning this up, I get 37,120. Of course you don't need this decimal here. We usually leave it out as it is assumed. Now before we jump into significant figures, let's talk about the terms accuracy versus precision. Although these terms are very similar to each other, there is a distinctive difference between them. So here we have an example of low accuracy and low precision, while this one has low accuracy but high precision. Here we have high accuracy but low precision, and finally this one, high accuracy, high precision. So looking at these pictures, what do you think is the difference between accuracy and precision? Well, accuracy describes how close your data points are to the true value. So these shots are close to the main target, and these ones are definitely close to the main target, while these two are far away from the main target for the most part. Meanwhile, precision refers to how close your data points are in relation to each other. So how close are they clustered together? So over here they're closely clustered together, high precision. Over here they are closely clustered together, high precision. But over here they are kind of all over the place. They're not clustered close to each other, and definitely not here either. So that's why it's low precision in both these cases. Alright, so accuracy refers to how close your data points are to the true value, while precision refers to how close your data points are to each other. So even if you did hit the true value, you still wouldn't know because your data points are so far apart from each other with low precision, it's hard to determine which one is the accurate one. Meanwhile over here, while you're close to the true answer, because your data points are all over the place, it still gives you a difficult time guessing which one is the true answer. Whereas over here, high accuracy, high precision, that's definitely what we're aiming for. To that end, scientists use significant figures to inform the reader about how precise or accurate their calculations or values are. Let's take a look at these 3 tools that we use in the lab. All 3 are good for measuring volumes, but they have varying levels of accuracy and precision. So beakers are good for mixing chemicals together and pouring them out, but they're not great, not super accurate or precise when it comes to measuring volumes. That's why it actually says approximately 100 milliliters. Most beakers in our lab typically say plus or minus 5% deviation. So if I fill this beaker up with 100 milliliters of water up to the 100 ml line, because it's only accurate to plus or minus 5%, not very precise, when I fill up to the 100 ml line, it's anywhere between 95 mils and 105 milliliters. That's a huge variation. Whereas a graduated cylinder, it's not great for mixing things, but it is a lot better at measuring volumes. Now this is not a 100 ml grad cylinder, it's only 50, but let's pretend it's a 100 ml grad cylinder. Most of my graduate cylinders at school are about plus or minus 1% in terms of accuracy. So if I filled it up to the 100 ml line, it wouldn't be exactly 100 mils, it'd be anywhere between 99 to 101. A lot better than measuring with a beaker, but not super accurate or precise. If you want precision, if you want accuracy, you want the volumetric flask. Now this one is rated at 100 milliliters, and you'll notice it only has one graduation line. While the graduate cylinder has multiple lines of graduation, and the beaker also has multiple lines of graduation, the volumetric only has one. This one specifically only measures one volume, that's 100 milliliters, but it measures it very, very well. It is typically accurate and precise to 0.01 of a milliliter. That's 0.0001% deviation. So 3 different tools, all 3 used to measure volumes, but a wide variety of accuracy and precision. So imagine if you had 3 students and you asked all 3 students to measure 100 milliliters, but one was using a beaker, one was using a grad cylinder, while one was using a volumetric flask. Now, if I added up all their volumes, it should be 300. But would it be accurate and precise to 300.00 to 2 decimal places? Absolutely not. While the volumetric flask is super accurate, the grad cylinder loses some of that precision, loses some of that accuracy. This hundredths column is an unknown. Because it has a deviation of plus or minus 1%, I don't know what this value is. Same thing with the beaker. Even its accuracy in the ones column is questionable. So if you have 0 plus a mystery number, does that equal 0? No. So that ruins my accuracy right there. I can't trust this whole column. Over here, I've got one mystery number. So even though I might be, confident with this number and this number, I have no clue what this number is. So 0 plus a mystery number, well, I have no clue what this number is. I have no confidence in it. So there goes even more accuracy in my calculations. Now, I'm fairly confident with this number. It's 100 something. I'm fairly confident with this number. It's 100 something. But over here, it could be 101, or 102, 97, 98. I have no clue how accurate this value is. So once again, I've lost even more accuracy. So I can no longer tell my reader that the total volume is 300.00 because I can't trust most of these numbers over here. I'm not confident with them. And that's the whole point behind significant figures and all these crazy rules that we're about to learn. We need to be able to tell the reader how significant, how accurate, how precise the measurements we're using are. And in the end, we're only as accurate as our least accurate measurement. It doesn't matter how good these two measurements are. If you have to use the third one that's not accurate or precise, it ruins your whole calculation. So we have to have a way to tell the reader how trustworthy your values are, which is why we have these crazy rules for significant figures. All right, so first rule, non-zero numbers are significant. They are numbers that we can trust. So in this number here, 9.67, this is not a 0, this is not a 0, this is not a 0. So therefore there are 3 significant figures in this particular value. Over here we have 2 sig figs because there's 2 numbers that are not 0. Over here we have 7 sig figs because there are 7 values that are not 0. However, if I wrote 3,000, this number is ambiguous. There's only one non-zero value, so this number is not particularly trustworthy. We say there's only one significant figure here. Or if I did something like this, there'd be 1, 2, 3 non-zero values, so 3 sig figs. Now that was the easy part. The rest of the rules deal with what happens when there are zeros. When can we trust them, when do we not? Well, Rule 2 states that any zeros that are between 2 sig figs are also sig figs. Since the 2 and the 7 are significant, because of rule number 1, they're not 0, therefore anything in between is also trustworthy. So this one has 4 sig figs. This 3 and these numbers over here are non-zero values, so they're significant. Therefore anything in between is significant. We have 5 trustworthy values. But what if I did this? Well, rule 1 says I can trust the 2 and the 2, and rule number 2 says, because this one's between them, I can also trust it, but this 0 is not trustworthy. So this value has 3 sig figs. Now the next rule deals with terminating zeros. To be a terminating 0, it must be the final digit in the number, and it must be to the right of the decimal place. So these zeros over here are not terminating zeros. This one isn't to the right of the decimal place, nor is it the last digit in the number. These ones are not terminating. Even though they're to the right of the decimal, they're not the last digit in the number. But this one is the last digit in the number, and it is to the right of the decimal place, so it's considered to be a terminating 0. So rule 3, this terminating 0 is significant. Rule number 1, non-zero values are significant. And rule number 2, any zeros between significant values are also significant. And so we have 3 sig figs in this particular number. So if I write 2020, I know these two are significant because of rule number 1. This one is significant because it's between 2 sig figs, rule number 2. But this one is not significant. It's not a terminating 0. Yes, it's the last digit of the number, but no, it's not to the right of a decimal. So as written, there are only 3 sig figs right now. But if I did this, now we have a terminating 0, last digit in the number and to the right of the decimal. And rule 2 of course states, if it's between 2 sig figs, it's also significant. Now suddenly I have 5 sig figs in this number. Over here, none of these are terminating zeros, none of these are significant, there's only one sig fig, which is the 2. Now the final rule states that counted and defined numbers have infinite significant figures, so they do not affect your sig fig calculations and you don't have to worry about factoring them in. So when we say counted values have infinite significance, what I mean is that this 2 has infinite sig figs, not just 1. That's because this 2 is not a rounded number. It's not like I had 1.999 people and I decided to round up, or I had 2.00001 people and I rounded down. No, this is 2.00000 forever. We don't have fractions of a person. You're either 2 people or 1 people, nothing in between. So that's why this one is an infinite significance, so we don't have to worry about this one impacting our calculations. The same goes for defined numbers, like the word dozen. The word dozen means 12. But that's not 2 sig figs, it's infinite sig figs. Because when I use the word dozen, I don't mean 11.99999, I'm just rounding up, or 12.00001, I'm rounding down. A dozen is exactly 12, 12.00000 forever. Same with calculations. So if I wanted to calculate the area of a triangle, the equation is base times height divided by 2. Well, this 2 doesn't have 1 sig fig, it has infinite sig figs. Because the equation isn't base times height divided by 1.99999, or 2.0000001, it's base times height divided by 2.000 forever. This 2 is a defined number. So essentially, we're only concerned with measured values. So how do we use these sig figs in our calculations? Well, let's take a look at it. When it comes to adding and subtracting, it's pretty straightforward. Just take the value with the least number of significance in terms of the decimal places, and that is what your final answer should be. So when you look carefully over here, I've got a super precise value of 5.2631, but no one else is that precise. So because I don't have values for this column over here, that wipes out all my data. I can't use this value over here. Same thing, I'm missing a number over here, so that wipes it out. Don't worry about that. And now I can start worrying about these values. These ones are trustworthy. These values are significant. So I am confident with this as my final answer. If I had included these 2 digits in my answers, I would be lying to the reader. I'd be saying, yeah, trust me, I am accurate all the way down to this decimal place. But that's not true. I can't trust these values. So my final answer must be expressed as this, 24.61, because that is all that is reliable. These last 2 digits are unreliable and should not be passed on. Now what happens if you're multiplying or dividing? Well, your final answer should be rounded to the least number of sig figs in your calculation. So over here, 3.46 10 to the power 7, I only have 3 sig figs, all of which are due to rule number 1. Over here, I also have 3 sig figs, all of them due to rule number 1. Since both of them have 3 sig figs, my final answer should only have 3 sig figs. So I can only trust the first 3 digits. So in this case, I would write down 617. So I'm going to round this 6 up to a 7 because of this number over here to the right is greater than 5. And then from there, fill in zeros for the rest of the values to show that I can't trust these numbers over here. So if on a test you gave me this answer, typically people just punch it into the calculator and just write whatever's on the calculator, you are lying to me. Because you're lying to me, I'm deducting marks. You must tell me how many of these values are actually significant, how many of these values are actually trustworthy to get the full marks. So if on a test you gave me a value with too many sig figs, more than should be there, I would have to deduct a half mark. Because you're telling me I can trust those digits when I really cannot. Let's do this next one really quick. We have 4 sig figs here, 5 sig figs here, 5 sig figs here, and here. So I'm only as accurate as my least accurate measurement, in which case this is a 4, so my final answer should only have 4 sig figs. So I can only trust, oh, this is kind of out of the way, these 4 over here, which would be, I wish this thing would move out of the way, 13.39, but because of the 8 next to it, I can round it up to 13.40. Alrighty. Now the last topic we need to talk about is metric conversion. This is an international system of units, often called SI units because in French it's Système International. These are the units that all scientists around the world have agreed to use in order to minimize confusion when you're moving from one measuring system to another. If we all have a standard measuring system, then we don't have to worry about mistakes due to conversion factors. Now the metric system is very versatile. It can be used for measuring length, mass, volume, time, energy, pressure, so many different ways to use it. And all it is just moving the decimal place. So it requires you to know the prefixes. Mega, so megabyte for instance, means 1,000,000. Kilo, so kilometer, means 1,000. Then there's hecto, deca, deci, centa, milli, micro. And there are a lot more beyond that. I mean, we talk about gigabytes and terabytes worth of data, right? But these are the ones that we'll be working with most of the time. And of these, you'll probably only use these 4 for the most part. So let's try converting 352 centimeters into kilometers. Well, our starting point, centimeters, is over here, while kilometers, our end point, is over here. And in between, we're going to make 1, 2, 3, 4, 5 jumps to the left, which means I'm going to have to move my decimal place 5 jumps to the left as well. 1, 2, 3, 4, 5. Then fill the empty spaces with zeros. Then we'll clean this up. And now our centimeters are kilometers. Well, what if I want to convert 0.000712 hectoliters into milliliters? Well, we start off with the hectoliter, and we end up with a milliliter. And that will require 1, 2, 3, 4, 5 jumps to the right. So I'll move the decimal 5 jumps to the right. Let's clean this up. Get rid of the zeros in front. And our hectoliters are now milliliters, 71.2 milliliters.